Hi, welcome to the Signal Pad, and check out what I have here today. This is the Tektronix 2 Series mixed signal oscilloscope, which will be announced any day now, and it comes in a bold new form factor, making it extremely portable, and also has a battery option, which I don't believe it has been released yet, but it can also be battery operated. It does have a VESA mount in the back, allowing it to move around in its chassis, as well as be mounted, of course, on anything that has VESA compatibility. Now, one of the things that I got really excited about this is that this is essentially the entry model to the very capable 4, 5, and 6 series oscilloscopes, which I've all done reviews and teardowns here on the channel, which means that the software, which is fantastic, has been ported down at this level, and almost all the functionalities of the higher order are preserved here. Obviously, some of the high-end functions like DDC and some of the sophisticated TSP stuff is not there, but essentially it's an identical GUI, which means that this is going to have all those fantastic GUI functions and rewritten from scratch essentially by Tektronix a couple of years ago and has been refined ever since. So this is the highest end model of the 2 series, and there's a lot to talk about. I want to talk about its internal construction. We'll do some tests with it. I haven't had it for a very long time, but so far I've been fairly happy with it. It does have some shortcomings which we can talk about, but look at it. It's pretty cool looking. So let's dive right in. So let's take a close look at the 2 series here. Now this is obviously a 4-channel oscilloscope, and it can be optioned from 70 MHz all the way to 500 MHz, and it has a 1.25 gigasample per second on all 4 channels, or 2.5 gigasample per second on only 2 channels, and that is an 8-bit architecture with 10 million samples of memory. Now the input impedance to the oscilloscope is actually fixed at 1 mega ohm in parallel with 13 picofarad, which means there is no 50 ohm termination option. Now that can cause some problems, especially for the 500 megahertz model, and there's a way around it. We're going to do some experiments and explore that. If you also note, there is no ×10 probe detection. That's because this is using a single PCB architecture, and that doesn't go high enough to reach the base of the BNC. We will see that during the teardown, so it's something that you need to be aware of. You're going to have to set that essentially yourself. There's an auxiliary input for trigger, of course, and there's an arbitrary function generator which can load arbitrary waveforms, which is fantastic. 50 megahertz is the maximum frequency, and it has an auxiliary output that can be programmed, which can be used for following, triggering, and things like that. There is also a probe calibration, of course, and a 4-bit pattern generator, which is programmable through the firmware in the future. I just wish this connector was female rather than male, because those pins, I think, are a little bit easier to break in the case of a male connector. The screen is really quite nice, multi-touch capacitive, of course, and it does look reflective, but it's actually not that reflective in person. It's a little bit difficult to film it with the camera, but I'm quite happy with it. It's nice and bright, as you will see in a second. Now, this does not have an internal power supply. It has a brick outside, which connects here to the side, and that's one of the reasons why it's easy to actually have this battery powered ultimately, because everything internally is running at DC, with DC-DC converters, of course, but the input is just 24 volts, I believe. And all the connections and everything is in the front. Nothing unusual going on there. And this is totally flat, so all the buttons are underneath the label essentially. And it has a base that's sticky, so it sits really nicely on the table. They obviously thought about that very carefully. And because of the VESA mount, you can tilt this so it can be completely flat. So if you have it high up, let's say on a bench, you can still see it reasonably well. And on the right side, there are the USB 2.0 connectors and Ethernet as well. And it can do VNC over everything, which I will show you in a second too. I think it looks really nice. It really is a bold approach from Tektronix, and its portability is fantastic. I think it will have a lot of interesting use cases, especially if you have it on like a swiveling arm because of the VESA mount, and it's so lightweight and it's completely silent when it's running. So those are excellent. And the digital inputs here are also on the right side. They're not enabled right now through the firmware, but eventually it will be. This is a very early version of the firmware that I have, but it's accessible with a special cable on the right side. So let's take a look at the acquisition board inside of the Tektronix 2 series. Well, this is really actually more than the acquisition board. What the tech engineers have done is that they have reduced the entire oscilloscope to a single PCB. And this makes manufacturing quite easy and lowers the cost, because all you have to do is wrap a case around it, put an LCD in front of it, and that's your oscilloscope. Everything is contained on a single board, even the buttons and knobs that control various settings of the instrument. There are also some disadvantages of that, because you have to make some compromises since you only have one board. But it does make this entire thing extremely thin, because everything again is contained. There's nothing overlapping on top of each other. But I did want to go over the hardware architecture and talk about the pros and cons of this. So let's talk about the inputs. So we have channel 1, 2, 3, and 4. We have the auxiliary input, which can be the trigger, as well as the auxiliary output and the AFG output. Now I went ahead and I took the cover off of a few of these connectors so we can see what's underneath them, and also we can examine the structural integrity of this. Now whenever you solder one of these connectors, which have a lot of user interaction with, this is your input of your oscilloscope, to the PCB, you have to be quite careful, because otherwise strain and stress over time will certainly damage that connector. And I think what they've done here is excellent, because they have this custom-made bracket over here, which not only acts as a shield, shielding the various stages from each other so there's no interference between the channels, but it also clamps this down to the PCB from multiple points soldered onto it in order to make that connection very strong, and is bolted down, as you can see. So I'm really quite happy. Often these single PCBs can have this as a failure point, but I think they've done a good job at protecting it here. So the front-end IC of an oscilloscope is pretty important, because you can use the greatest data converter in the world and it wouldn't matter if the signal is already damaged before it reaches a data converter. And the front-end IC is responsible for single and to differential conversion, various gains and attenuation control, as well as, of course, triggering. And the Tektronix is using a custom chip that they made themselves, and high-end instrument makers typically do this. And this chip will handle all of that analog processing for you. Now these channels do not have a 50 ohm input, but I believe that this chip could support it and switch into it if necessary. But it does have the output which goes into the data converters, as well as the slicing and the adjustable thresholds for the triggering, which goes into the triggering processing, which I think is handled by the FPGA. And it's interesting to see that on the auxiliary input, they're using exactly the same IC, but most likely they're not using all of its capabilities. But it doesn't matter, because this is their own chip, so they can just throw one more in there to simplify the design, and probably it will be even cheaper for them to do that. But these four channels are essentially identical. Now if you look closely, you can see a couple of LC components here, 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 and here, and you can see the differential traces going into the ADC inputs of these two chips, which I will talk about. These LC filters are most likely anti-aliasing filters, blocking everything they don't want before it goes into their data converters. And by the look of it, I believe all of these are built with the highest bandwidth. And the lower bandwidth versions of these oscilloscope are probably software locked anyway. So we should be able to take a look and see if there's any way to go around that, but I would be skeptical, because I think a lot of these components now use trusted platform chipsets and they have encryptions in them. So after the anti-aliasing filters, we have our two data converter chipsets. These are ADC08D1520 from Texas Instruments, which are low power, 8-bit, 1.5 gigasample per second dual ADCs. You can also run them at 3 gigasample per second using one channel, which again is a typical thing, because they do have a front-end mux and sample and hold, which can only use one of its inputs and then run it at the full rate. And this is what happens in this instrument as well. But they're not running these at their maximum capable sample rate. They're running them a little bit slower at 1.25 gigasample per second and 2.5 gigasample per second when you're using only two of the channels. Now these ADCs have fairly good performance, even at 748 megahertz input, which is already above the frequency that you would be using in this scope. They retain a 7.4-bit ENOP, which is typical from these chips themselves. Assuming that the tank front end is very good, which I think it is, so you should be able to get about 7.5 bits of ENOP or so at the 500 megahertz input, which is the maximum this guy will do, which is still pretty good. Now the data captured from this running a little bit slower makes the job of the Xilinx FPGA a little bit easier. There's less data to worry about, but everything is handled through the Xilinx Zinc Ultra-Scale FPGA here, which these are actually quite expensive. And the data is captured and processed and decimated in high resolution mode, and all the triggering and everything is handled here. There's lots of memory available, and I believe that the display and everything is also being driven by the Zinc as well. These FPGAs are now so sophisticated that there's a lot you can do on them. Now the clock for the data converters is coming from this chip, which is also a Texas Instrument LMK5B12204. This is an ultra-low jitter network synchronizer clock, they call it. It has an analog PLL and a digital PLL built into it. It can generate multiple clock domains with extremely low jitter and synchronize everything. This is typical to find. Now these are pretty important, and the fact that they're using a TI part probably means that there's a family of components that TI recommends in order to retain the best jitter performance from these ADCs. If you put a bad clock in an ADC, it doesn't matter how linear it is, the effective number of bits is going to go down the drain anyway because of the jitter of the clock. So this collection here is well engineered. There's a lot of DC-DC converters and various analog signal generation nearby to ensure that these things all have a good power supply. Lots more DC-DC converters over here. On the other side of the board, there's a battery real-time clock in this area as well to make sure that it obviously retains the time if things are turned off. Now on the right side over here, we have another chip. Now this is a kind of a mystery chip. I couldn't find any indication of what it is, probably also made by Tech. It just has a part number that starts with AGD. And I looked around and the only reference I could find to it was in a document for an MDO from Tech where they talked about how you can wipe the instrument completely clean. And this probably has some memory in it as a result that they were pointing out that this is for military applications and so on. So I suspect that this is basically an arbitrary function generator chip with built-in memory and DAC and everything. And it looks like the output of that goes into this chip over here. Now this is a differential to single-ended converter DAC output driver, which again makes sense because your arbitrary function generator output is single-ended. So this processes and produces the data, converts to single-ended, and eventually reaches over here. There's a relay in here for range switching, most likely, and I'll show you what's on the other side as well. There's a fuse on the AFG, which is fantastic. So if you damage it, you can actually repair it. Now in the logic analyzer input, we have a couple of chipsets here which buffer the inputs into the logic analyzer, and unsurprisingly, these are high-speed comparators. There are 4 of them in each chip with 700 picosecond capability. These are LMH7324, also from TI. So they're essentially using TI parts everywhere. There's another comparator here, which is even a higher performance one, single channel, and that probably is used for the triggering. It's because of its close proximity to this. Also has very, very fine and fast edge detection and pulse detection, which is something you need for fast triggering, of course. Now all of these knobs are controlled with various bus expanders and serial to bus converters. These are just basic stuff to control the rotary switches and the buttons and everything. And we have a couple of chipsets over here for host and device USB. These are all USB 2.0. There's no USB 3.0 on this, and there is a network Ethernet controller here as well. And that's really everything that's on here. Now one other quick comment over here, this area that you see that's completely empty is supposed to be for the power supply, but this is a DC input. It has some advantages, of course, because you can run it from a battery, which I think is probably something they would do, but you can also put an AC supply here if you want to in the future, because there's enough space for it, so they can just plug 110 volts in. And that's a compromise to be decided depending on how they want to run this and no noise injection into the rest of the board, as well as how they want to run this on the battery. And here's the back of the board. There are a lot of passives in there as to be expected, and a couple of other important components. We have our backup battery over here, but here looks like the LCD connection for the front LCD screen, and here seems to be a connector for the battery. So there's something that you can probably plug a battery into, and a few other interfaces around. Here's the fuse I was talking about for the arbitrary function generator. Pretty useful to have something like this. You still have to open it and replace it, of course, if it goes bad, but at least you do have that option. A few other protection circuitry over here. Now, one last comment I wanted to make. This is a single board, complete oscilloscope. Now, it sounds easy on the surface, but if you're building a high-performance device with all the switching and all the digital activity and the DC-DC converters and FPGA that sits in there, the noise distribution on this is actually quite difficult to manage. So the fact that they have managed to do this, and we can test it and find out how well it does, but generally speaking, it's not that easy to actually squeeze everything onto one board. There are compromises to be paid. Again, this is Tech, so they're taking care of that, I am sure. So enough of that. Now let's go turn it on and take a look at it. So for our first experiment, let's investigate the 1 megaohm input impedance and its impact on a very broadband signal. Here I have a very long SMA cable connected directly to the input of the 2 series. Now I'm generating a multi-tone signal spanning from DC to 500 megahertz that's already been calibrated to be of equal amplitude right here at this connector. And that's being generated here up here by a Keysight M8190A, which is a very good arbitrary waveform generator. So we have that going into the channel 1, so we can take a fast Fourier transform of this and take a look at the amplitude response. And then we can use this pass-through 50 ohm resistor to emulate the effect of a 50 ohm termination. In that situation, the cable then sees the 50 ohm. Keep in mind that when the impedance is 1 mega ohm and the cable is very long, the impedance looking into the cable can actually rotate all around the Smith chart, and it can be a variety of impedances through the entire bandwidth of the oscilloscope because of the length of the cable is beginning to be comparable to some of the wavelengths that are present in the cable itself. So let's go ahead and try that. Now I've also connected this to a router and I'm wirelessly going to VNC into this, which is natively supported by the 2 series. The 2 series also supports a mouse if you want to use a mouse on it, which is really convenient, but we're going to use a remote desktop so that we can see this screen much better. Let's give it a try. Okay, here we are. So this is the screen of the 2 series, and this is running a little bit slower than what the refresh rate of the actual instrument is, naturally, because it's still over the network. And as you can see, it's very nice and smooth. Everything looks great, and it worked the first time I tried it. All right, so first thing we need to change the probe. We don't want this probe to be times 10 because we are directly connecting it with a cable. So we can change that very easily from here. We go to times 1. Okay, that fixes that. And now We have to change the scale a little bit as well, so we can get a nice signal. Let's say something like that. Actually, maybe a little bit too large. Here we go. So now I want to take an FFT of this, so I can see how flat those tones are, because according to the ARB, it should be completely flat all the way past 500 megahertz. So we're going to go over here, and we're going to add a new math function. And it's going to automatically create a new screen here. Now we want an FFT of the channel 1. It's going to do that automatically as well. And just like that, we have our FFT. And it looks reasonably good. We can go ahead and change our horizontal timescale a little bit, so we can get a bit more resolution on our FFT. I think we can do something like maybe 4 microsecond. And you can see it does a very good job. So it's running at 2.5 gigasample per second, and it's recording about 100 kilopoints, and it's very fast and quick. This is an FFT done raw, and this tone over here this is from the instrument itself, and this is above the 500 megahertz bandwidth. It's probably a tone generated by the ADC. So you can see it's roughly around the sampling rate divided by 4. So let's put some markers on this so we can see how much drop we have. And you can already see that this frequency response is not flat. And that's because, again, we're terminated into 1 mega ohm with a very long cable. So we can turn on our cursor. We can drag that over here. Let's say somewhere at the beginning. Okay, here we go. Perfect. So I got a tone here at around 13 megahertz as, let's say, our initial starting point, and a tone at 503 megahertz, which is right around the bandwidth of this oscilloscope. Now we're starting at about minus 29 dBm, and we go to minus 35 dBm. So this is more than 3 dB of drop, considerably more than that. And that's because, of course, we have some additional attenuation because of the fact that the input impedance and the cables are long. So now that we can see this, and by the way, this cursor is really easy to use, and you can use your mouse scrolling up and down to move it around. It looks very good, and they really have thought a lot about this GUI. I'm quite happy with it. So let's go ahead and now change it. I'm going to put the pass-through 50 ohm resistor in there, and let's see if it makes a difference. And the pass-through has been added, and you can see already that we have a 3 dB drop now at 500 megahertz, which is what we expect. Now we can make the vertical spacing a little bit more favorable, and that again changes because, of course, you're terminating into 50 ohms. Now we don't have a perfect flat response here because I'm using an external 50 ohm and it's not calibrated with the input of the instrument itself, but it does give me a lot of my bandwidth back. And here also you got to see a little bit about the FFT and how easy it is to manipulate the menus in this instrument itself. Okay, enough of that. Let's now try some basic tests on the oscilloscope. So next we're going to use this digital or mixed signal board to create a few things where we can look at with the 2 series. These signals may have anomalies or other imperfections that we want to hunt for and find using the capabilities of this unit. So we have a sequence of pulses here being captured on channel 1, and we want to analyze it. We got to first set up our trigger a little bit better, which we can easily just drag up over here to the middle. Now as soon as I do this, we're going to see some overlapping waveform, and that's because the trigger is on a simple rising edge, and sometimes it catches the first one, sometimes the second one, and so on. So it's going to have this effect. This is quite normal. Now I can also stop the trigger. I can do another one, and sometimes I can see the overlapping effects here. Now I can't figure out how to do a single capture. I don't see that actually available here. I can only stop and start it. Maybe that's something they can add to the GUI. So first thing is, let's add some hold off so we don't see this thing jumping around so much. We can easily do that by going under the trigger menu here, and we're going under hold off, and let's set a hold off. Let's see what kind of duration we need. Well, it looks like these pulses are about maybe a microsecond long. So let's enter 1 microsecond here. 1 microsecond. There we go, and that should fix that. There it is. So it's no longer moving around, and it looks quite good. I can change the time scale as well. There's our pulses. Now this looks perfectly normal. Doesn't seem like there's anything unusual going on about it, and I can let this run for a long time and we really wouldn't notice anything because the anomaly that's happening is really rare. But let's say that you didn't even know if there was an anomaly. Is there a quick way to figure it out? Well, let's do an FFT on it and see what happens. There may be some effects that we can capture using that. So here's our FFT. Okay, good. So let's look at the signal at a much longer time scale. We can go way out, something in the millisecond range. There we go. Now if you look at this, you can see that something happens to the FFT every once in a while. So there is something on this waveform that appears that shouldn't be there, and that causes the frequency content, which is very periodic, to have these skirts, and that's because that pulse broadens the actual frequency content around the main tones that are present. So there is indeed something going on with this waveform that we need to analyze. Okay, this kind of tells us a little bit, but it doesn't really tell us what that problem is. Okay, so let's go ahead and turn this off. We don't need this. Okay, you can actually drag it and drop it down, I believe, and it goes away. There you go. Quite nice. Really, they've thought about this a lot. Okay, let's zoom back in here so we can see that waveform. Let's see if we can find something that could be a runt. So let's go under trigger, and let's change our triggering from edge, and let's look for a runt. Okay, and this gives us now two levels that we can trigger on. And if there is a pulse that's smaller than another pulses, or if a pulse that doesn't quite make it where it should be, you can catch that. This is really common actually, because every once in a while you can have a bus contention or something like that. When two signals are fighting, the amplitude of the signal actually goes down. This can be very handy. So we can set these upper and lower limits. Actually, we can set them manually over here. So let's put one up here. Let's put the other one down here. And let's go and change this to a normal mode of trigger, as opposed to automatic. There's normal, and check it out. There it is. Right away we can catch that. And if you look at the triggering, you can see how slow that is, because this happens once every 800 or 900 millisecond. Now 800 or 900 millisecond, when you're sampling at 2.5 gigasample per second, is a lifetime. It's a very, very long time for this pulse to be happening. There's also another anomaly that you can see that happens right next to it. That anomaly is when the pulse is shorter than the other pulses. We can also trigger on that separately, because if you go under trigger, you also have a whole bunch of capabilities you can do a pulse with, and you can catch that pulse instead of catching the runt. So there's actually two anomalies happening on this at the same time. Now what you can do over here is you can also go on act on trigger, and because this trigger is very infrequent, let's say instead of it happening once every 1 second, it was happening once every day, that you really can't sit in front of it and watch it. What you can do, you can create an action on a trigger, and there's several triggers that you can set up, and you can tell the instrument what to do if that condition is met. You can save the waveform, you can screen capture, and so on, which can be super helpful when you have a problem that doesn't really show up very often. And you can also specify a maximum, so if it happens very regularly, you don't just run out of memory as a result of that. So the triggering, as you can see, is a fairly good and advanced for an entry-level oscilloscope. It's comparable to some of the higher frequency models they have, because it's a ported software down into it. So next, let's take a look at the output of a DAC that is unfiltered. So here I have the output connected to channel 1 again, and you can see that there's a DC offset on this signal. So let's first of all get rid of that by setting this to an AC coupled signal. Now, this is a very slow DAC output. You can see we are only at 1 megasample per second and in 20 millisecond steps. So we really don't need 500 megahertz of bandwidth. We can reduce the front end noise by filtering that digitally. So let's set that to, let's say, 70 megahertz. Actually, we can even go down to 20 megahertz. Okay, so that looks good. We can see our waveform a little bit better here. Now let's zoom in a bit more to it and see what it looks like. So we can kind of see the steps of the DAC. That's because this DAC is unfiltered, so we have the actual digital steps being shown up. This is not a very high resolution DAC. And every once in a while we can see an anomaly on it. But I want to look at this a little bit better. We should put the oscilloscope into high resolution mode, especially because the signal is slow. We can take advantage of the oversampling and then getting the 16-bit resolution. We can do that in the horizontal here, in the acquisition settings. We can go ahead and change that from sample to high resolution. The instrument, of course, also supports peak detect and envelope and averaging as well. Now, keep an eye out on the waveform. As soon as I go to high resolution, you can see how much better it looks in terms of obviously having much more vertical resolution. We can see the fine details of the waveform. And by the way, I found a single sequential acquisition button is actually over here. Even though you can't do it from down here, you can do it from this. So that's not actually missing from the firmware. Let's go ahead and zoom in a little bit more now. And first of all, you can see clearly the steps. There's a little bit of filtering on them, but there you can see them switching between the different digital settings. Now, if I also pause and do a capture, you can see every once in a while, at least on every cycle, there is a little bit of a blip on the waveform. And that blip is because a code is being skipped in the DAC output. So we're jumping over 2 levels as opposed to 1 with every clock cycle. So you can again see, using the high resolution mode, if the signal is slow enough, you can catch some really subtle details using that method. The 2 series, of course, supports several different bus decoding algorithms built into it. Now, the digital interface, the logic analyzer, isn't enabled yet in this firmware, but we can use it on just the regular analog channels. So what I have here is an inverted UART signal on channel 1. Now, UART is a single wire, so we should be able to decode it fairly easily, and you can see some data is going through. And I don't know what that data is. I want to find out. So first, let's trigger a little bit in the middle of it. So there you go, there's a lot of randomness. Again, the display on the instrument itself is much faster than what you see here. So some of these artifacts are not from the unit, but just because of the remote VNC interface that you're looking at it. So let's go over here and let's go and add a new bus. Now, as soon as you do this, it opens up this display for us, allowing us to choose what kind of bus type we have. And there's several of them that are supported here. This we know is an RS-232. Okay, we set that. So now we need to set the threshold, and we can set the threshold to be about, let's say, 2 volts. Which we can see from the waveform up here. And we know that this is inverted, So you can see this inverted because it spends most of its time to be high. So we're going to invert that. And it looks good. So we should be able to, the data bit rate is actually 9600. So that's also correct. So we should be able to see what's being decoded now. Let's go, let's actually change that. Instead of hex, let's look at it in ASCII. There it is. There is our sequence. And what could it be? Well, let's create a table and find out. And we can create a table very easily in the same menu. You can turn the table on. So let's see what it says. So Tektronix enabling innovation. Perfect. Looks good. So there's a lot happening on the screen here, by the way. As you can see, there's multiple things happening. I'm actually quite happy with the speed of the instrument. Now we can also enable another channel just for the fun of it. Okay. And then we can go over this channel. And let's leave it as it is actually. Let me add a math function. I'm curious to see what happens if I add an FFT while it's trying to do this. Let's make an FFT. Okay, there you go. Look at that. That is a lot of stuff happening at the same time. This is actually an FFT on channel 1, not on channel 3. We can put it on channel 3. There should be nothing there. I just want to create a lot of traffic for the instrument to handle. There it is. All of this is taking an FFT of a different channel, is doing decoding, is showing the table, and it's very responsive. I have to say I'm pretty impressed. This is not the same as the 5 and the 6 series, of course, but it is still very, very good and quite usable considering how much stuff is happening on the screen. So let's try out the arbitrary function generator of the oscilloscope as well. Here I have a 50 ohm splitter that splits the signal from the AFG into two paths. One path goes through a filter and it goes into channel 1. The other path directly goes into channel 3. And I do have a 50 ohm termination in both of these because the entire system needs to run into 50 ohms. Now we can generate various waveforms from here and see the effect of the filter and see what happens and what are the differences between the two channels here on the scope. And we have our channel 1 and channel 3 on the oscilloscope here. So let's go ahead and turn the arbitrary function generator on. What is the set to? Sinusoid, 1 kilohertz. Let's make that 1 megahertz. Here we go. And continuous. There it is. Look at that. That's our 1 megahertz signal into 50 ohms, 500 millivolt peak to peak. And it looks good. And there's absolutely nothing coming into channel 1. That means that our filter is not allowing a 1 megahertz sinusoid to go through it at all. So we have to figure out what that frequency is. Now what we really want to do is we want a broadband signal. Now unfortunately the AFG built-in does not have a multitone, which could be quite useful in this situation, but there are some tricks we can apply later on. It does have a set of nice functions built in, and of course it has arbitrary, so you can create your own multitone if you want to without any issues. But let's choose the square wave here, because square wave has multiple harmonics and that could potentially help us. Okay, let's go ahead and enable that. Now, as soon as I enable that, we do see a little bit of something happening now on channel 1. So that's a bit encouraging. So we're getting some information. Let's zoom in a little bit more. There it is. So there's definitely something there. Now you may also ask, why does this square waveform look like this? And that's because the square waveform is also hitting the filter outside of its frequency of operation. So it's creating a really bad reflection and a bad standing wave signal. And that's why it looks like this. This is normal. It's because of the filter. The instrument's square wave is actually quite clean. Okay, that looks good. Let's go over to channel 1 here. Let's make that a little bit larger so we can see what we're looking at. And let's go ahead and measure something on this so we can figure out what frequency that actually is, because these frequencies are obviously not the same. So let's click on measure here. Now, this 2 series has a nice rich built-in set of measurement capabilities, both on amplitude and time, of course. Now, what we're looking for specifically is frequency. Let's go under time measurements, and you can see how much stuff there is there. Lots and lots of different measurement capabilities. Let's go ahead and add frequency. That's what we want. And take a look, it is a 15 megahertz signal. So we're putting a 1 megahertz square wave into it, and we're getting a 15 megahertz very, very small signal out. And that obviously means that multiple harmonics, the 15th harmonic of the square wave, is the only thing that's actually going through. So it means that this must be a really high quality bandpass filter. So we should be able to investigate that a little bit easier. That should be easy to do because we can go over here and we can change the frequency of the square wave and put that frequency to 15 megahertz. And that means we should get a very, very strong signal. And indeed we do. We're actually clipping. Let's go ahead and make that smaller. And too much. There it is. Look at that, 15 megahertz. And that is the largest signal. That means that this is a bandpass filter and with very high quality factor. Now we can again verify that even more if you want to. So instead of putting 15 megahertz, let's put 5 megahertz. If I put 5 megahertz, I should be able to catch the third harmonic. It will be a little bit smaller, but it should still go through, and it does. You can see it looks quite good. But if I put in 6 megahertz, I will see nothing because there are no there is no harmonic of 6 megahertz that lands on 15, and you can see again that it completely disappears. So it's all consistent. Even though this waveform looks a little bit ugly, it still has components only in the 6 megahertz and all of its harmonics. Now there is a trick we can play here. Instead of 6 megahertz, what we can do is we can add noise to it if we didn't know what frequency this was. So let's go ahead and add noise, and let's add a lot of noise. Let's add 50% noise to it. Okay, press enter. Now if I add 50% noise to this, there's going to be obviously noise broadband content everywhere. Let me make this a little bit smaller. Let's actually go over here. Instead of let's go to put this back onto 15 megahertz so I can show you something subtle. There you go. So this 15 megahertz square wave now has 50% noise on it. But of course, the sinusoid that's filtered out does not have 50% noise on it. And that's because most of that noise is broadband and is spread across all frequencies. And most of it is filtered by this. And this is one of the advantages of actually having a filter. If you have a really noisy square wave signal, you can capture a really reasonably clean sinusoid out of it if you have a very high quality filter. So let's go and put this back, let's say on something like 6 megahertz. Okay, and let's turn it into a sinusoid. Okay, so in this situation, what we have is a sinusoid with a lot of noise on it. I can take a Fourier transform of this and see what that looks like. Let's go ahead and add that. New math function, we're going to add an FFT, and that's FFT is going to be on channel 3, like so. Okay, now once we have it, most of this frequency content is of no interest to us. We want to really only look in this area, and we can do this because by double clicking here, we can create a non-auto scaled version of this waveform. So let's go over to start at 0. So we're starting at DC, and we can look at signals up to, let's say, 50 megahertz. Above that is really not useful to us. Okay, and we don't have enough resolution here, so we need to capture a lot more data. We can do that also reasonably easily. If I capture enough data, you can see that there's a main tone here. This main tone is at 6 megahertz, which is expected, and the rest of this is broadband noise. So that's what's coming out of channel 3. Now what's coming out of channel 1, you don't see anything in the time domain, but there's actually something there, and we can go ahead and change that, and we can put that on channel 1, and now we can see a tiny little tone over here at exactly 15 megahertz, and that is the frequency content of this noise that actually still passes through the filter. Now this is a very, very small signal, but you can catch it in the FFT. Now I can go ahead and reduce this, and it wouldn't really make much of a difference. You can see that that tone is still there. I have to now adjust the vertical spacing here. I think we need to go much, much lower. There you go. There it is. There's our tone. So this does have a reasonably good front end because we're catching that noise contribution of this signal, and you can clearly see the 15 megahertz. That's kind of a poor man's way of figuring out what that center frequency was, but you can also do it with a square wave, as you saw. And there you have it. I hope you enjoyed this quick review of the Tektronix 2 series. I haven't had this oscilloscope for a very long time, but hopefully I showed you some of its capabilities so you can get a general overview of what you can do with it. I don't have any pricing information on this, so hopefully you'll find out when it is officially released by Tektronix. I really do like the software. There are some compromises that obviously have been made on the design of this, so it's up to you whether you can use this in your lab or not, and it has some advantages again that I like, so I'm going to be certainly using it in my repair bench and moving it around the lab because of its portability. As always, I'll leave a link for this so that you guys can find it on the Tektronix website when it comes out. I get absolutely no benefit from the sales of this at all. This is a direct link. It's not even tracked. That's coming from my channel. But either way, let me know in the comment section if there's something else you want me to test with this. Obviously, the digital inputs are not enabled yet, but I'm sure they will be, and as well as the pulse generator over here. And it has some frequency counters and DVM capabilities, which are also not ready yet, which we can test in the future. So let me know what you think in the comment section. I'll see you next time.